to stop the set. Then we click start and auto. Let's change the PID setting. The gain is 1.2. PID is 0.024. Accept. Then the y-axis this one put to 120. Zoom in a bit. This one to 80. Then for the output is 30 to 100. 100 to 30. Now we can see the trending much clearer. So as you can see, there is a bit selecting a lot of overshoot. So now we want to remove the overshoot. First is we reduce the integral until the overshoot is minimum. So to reduce the integral action, what we do is actually we increase the integral time. Let's increase to 0.06. Then we create a step change of the set point. Okay. Concurrently, we change the derivative time to 1/4 divide the integral time by 4. So we get 0.015. Let's change the set point again. So there are still some overshoot here. So change again. This one increase further to say 0.12. Then this one divide by 3, so we get 0.03. Okay, change the set point again. So you can see actually the D is too high. So we reduce a bit, D to 0.02. So integral time is times 4. Change the set point again. So you can see actually the overshoot is worse than the when we put it at 0.012. So we revert it back to the PID setting at this point just now, which is 0.06. This is 0.015. So we revert back to the setting here. Okay. So we already done for I and D. So now we adjust the P until no overshoot. So we reduce to say 0.8. Change the set point again. Okay. So let's test again. This one seems to be okay. Okay. So another method for us to actually reduce the oscillation is by using another method, which is we look at the ratio of the integral time to oscillation period. So say for example, if that control loop is for flow or liquid pressure, so if the ratio is less than 0.1, so we put there. If ratio the integral time to period of oscillation is less than 0.1, we will increase Ti. Otherwise, we reduce gain. Gain. So then that. So let us look at the case study number 1. Okay, so we stop again, reset, then we put the looping auto, start, put the simulator in auto, then we change the T to 0.6 and the TI to 0.012. The D is 0.003. Okay, so the PV scale is 80 to 140. And the output is 0 to 100. So that is correct already. So we can see that actually the PV has a lot of unnecessary overshoot. So now we need to check, do we want to increase the TI or reduce the P first? So let's find the ratio first. What's the ratio of TI of period oscillation? So the TI we know that is 0.012 minutes per rep. What is the period of oscillation? Pause this, then try to zoom in to say 1 minute. So the period of oscillation is 568 minus 558, so which is 10. But this is 10 seconds, so just now 0.012 is minutes, so this is minutes, this is seconds, so second when convert to minutes, it must be divided by 6, so we get a ratio of 0.012 minutes to 1 over 16. 1 over 16 is 0.0166. So that gives us a ratio of 0.016.012 divided by 0.1666. So we get 0.0721. So since the ratio is less than 0.1, so we will need to increase the TI. So we know that actually the TI is the one that's causing the necessary overshoot. So we reduce the TI. Increase the TI to reduce the TI shown. Zero, 3. Okay, click update again, and we pump the set point. Okay, so blue is the PV, so it looks like it's okay already. But if we do not want even a single overshoot, we can further adjust it to say 0.05. The set point again. So now there is no overshoot. Right, let's try another exercise. So stop, reset, and we start. And put the loop in. How to change the P to 1.2 and the TI to 0.08 and D to 0.02. Okay, so the PV is 80 to 140 scale. Scale for the trending. And put it 0 to 100. That's correct already. So now we see here actually there is an oscillation. So we do the same thing. So what is the ratio of the integral time to the period oscillation? The time is 0.08 minutes. So what's the period of oscillation? So we need to pause this. Zoom in. So maybe zoom in a bit more. So the trending is behind here. So just scroll a bit to the right, left. Sorry. So from peak to peak is 555 minus 551, which is 4 seconds. So we need to divide by 60 to get the minutes. So now we get 0.08 minutes to the ratio of 4 divided by 60. 4 divided by 60, we get 0.06. So that is a ratio of 0.08 by 0.6. So we get 1.33. So since the ratio of the integral time to the period oscillation is not less than 0.1, it's actually larger than 0.1. 1.33 is larger than 0.1. So this is not true. We're not going to increase the TI. We're going to reduce the P. So let's update this again. We just change the P. So let us go to 1. Pump it up. Okay. Since the overshoot is getting lesser, we might as well put this one to 6. So we are getting less overshoot, so we can continue to drop again to 0.8. Except we need to pump the set point again. Okay. There's no longer any overshoot here. Okay. So by looking at the ratio, we'll know whether do we need to change the integral time or change the gain.